So the next lecture is named after Madame Wu Jianxiong, who is pioneer in experiment high energy physics, graduated from Berkeley and was in Columbia. So Wu Jianxiong was in Zhongyang Daxue, Nanjing Daxue now, and the award winner this time is Zhenan from Stanford University, who also graduated from Nanjing University. So I think it's very well fit to receive the Madame Wu Award. So Professor Bao's achievement is in soft bioelectronics is extraordinary. She pioneered flexible, stretchable organic semiconductors, laying the groundwork for electronic skin, material that match the durability, softness, and self-healing of living tissues. Her work on hair-thin sensor fibers like NeuroString allows minimally invasive connection with the human body to advance healthcare and neurotechnology. It will be great to listen to her. Her talk will be on electronic skins and NeuroString. So, think about it.
Thanks, Professor Yao. Let me see, is it on? Okay, thanks, Professor Yao, again for this extremely kind introduction, and also the award committee for selecting me for the Wu Jianxiong Medal. As Professor Yao mentioned, we share the commonality of from Nanjing University. Actually, there is a memorial for her on the campus for Wu Jianxiong in Nanjing University. But it was after I already left Nanjing that it was established. But she has been an inspiration for many scientists, including myself, for her perseverance and really the passion for pursuing science. So her legacy continues, and I'm really honored to receive this medal that's named after her. So for myself, I was trained as a chemist, more specifically organic chemist and a polymer chemist. So what I learned during graduate school was to learn how to make molecules. And very fortunate, after my PhD, I went to biolaboratories. That's the kind of the innovation hub for new technologies for telecommunication and networking. So that's where I started my career. And at that time, it was more than almost 30 years ago, before iPhone was even a concept. And the TV screen was still a huge box. But at that time, we already had a dream. The dream was to have grandmother and the grandson, when they talk to each other, they can see each other on the phone. But then that means the huge TV screen is not going to work out. And we have to squeeze the display into a sheet of paper. So that was the project I worked on when I was in Bell Labs, trying to make a new type of display that's paper thin. But then coming back to the fundamental science, what's lacking is really the materials that can make such a display. All our displays were made, and still nowadays, mostly made with rigid glass and also silicon. So it's not possible to make displays that's bendable and foldable to place on the telephone set at that time. So that motivated a lot of new science. That's the kind of the early work I got into, basically understanding from the molecular level how we can develop a new generation of electronic materials, semiconductors specifically, that can have ability to make switches, make transistors, just like silicon. So that kind of material allowed us to actually build the first foldable display by the time I was leaving Bell Labs after 8 years. And that was also a great learning process for me about thinking about how to define problems. So when I got to Stanford, I thought displays, flat panel displays was already something industry was pursuing. So I should be working on something further away, not trying to compete with industry, but rather maybe define a new direction for industry. So I was inspired from talking to colleagues. I was inspired by the sensory function of human skin. But as a materials chemist, immediately the way I think about human skin is not just the functionality, but as a material, it's flexible, stretchable, biodegradable, and self-healable. So at the time, we already had flexible electronics in sight, but electronics that carries the properties of human skin and have large sensory functions. They did not exist. So I thought this could be a direction that I could be working on for the next 20, 30 years in my career, because this, again, sets up the fundamental questions about what kind of materials can we use for this new generation of electronics. They did not exist before, but that's exactly what I want to be working on to really fill this gap of fundamental knowledge. And of course, these kinds of devices, if we're successful, they could potentially also help the society, help human beings, because they can help patients who lost sense of touch, potentially to regain sense of touch, or maybe for robots to be able to feel and to be safer among the humans. And furthermore, there are a lot of medical devices already existing, and we're using them today, but they are still very rigid and brittle and difficult to get close to human body. So if we can make sensors and electronics just like human skin, then potentially we can open up new possibilities for understanding human health. That is to have sensory systems covering the surface of our body or even go inside the body, but without us really feel it, without damaging the human body or cause wounds, but they're comfortable, invisible, imperceptible, biocompatible, and also autonomous for collecting information at the same time. So this is the electronic skin that we hope to pursue, but also at the same time, these electronic skin, they also need to have some level of computing capability, just like our human skin. Actually, we think about our functions and also actions comes from the brain. But actually, a lot of information has already been processed at our peripherals and then feed the information to the brain. The brain is the central hub. Same with the human skin sensory system. So in this case, the sensors, these are the mechanoreceptors under the skin. But really interestingly, they encode the information into this frequency signal, basically spike train signal that can transmit over very long distance through the nerve to get to our brain. And not only that, this kind of spike train signal is very important because counting the number of pulses it's much easier to be accurate comparing to getting the amplitude to be correct. So traveling for the signal to travel long distance, they would not lose the important information. And furthermore, these spike trains are encoding information in frequency domain, but also in the time domain. So combining these spike train information from various different mechanoreceptors, some can sense temperature, some sense the pressure, some sense strain, or some sense vibration. But all these mechanoreceptors, their signal actually gets combined at the synaptic junction, and then they combine further through different nerves, and then eventually travel through the major nerve to get to our brain. So this signal already has some patterns that are pre-processed for our brain to be able to recognize. That's why we don't need to consume a lot of power like what the GPUs need for the AI algorithms, but our brain can actually process a lot more information using the simply these different patterns and learn from the different patterns. So our electronic skin, in our electronic skin, we also hope to incorporate these computing capabilities into the sensory system. So that is the e-skin that we are hoping to pursue. That is the sensory system that mimics the human skin materials property, but at the same time, they have sensory functions and the computing functions all combined into these new form factor. But at the same time, be able to collect information and eventually also wirelessly communicate information seamlessly. So here in my talk, I want to give you I already give you the motivation, why we're trying to do this, and the overview. And now I will go into a little bit about the fundamental chemistry and material science that we have learned along the way to enable this new area of research and new area of technology. And then I'll show some possibilities for using the electronic skin and also going towards the future. The NeuroString, which is basically the rolled up e-skin, taking advantage of the materials property of the e-skin. So electronic skin actually can be made in different ways. There is the engineering way of making electronic skin. There's also the materials chemistry approach, which is what we are taking. So from engineering point of view, it's actually possible to also make electronic skin by taking existing materials, but make them very thin and design into these conductors. So these are wires of metal, or can be silicon as well. But metal or silicon, they are very brittle and rigid. But if you make them thin, they become bendable and even flexible. But if you incorporate these kinds of special physical geometry, you can actually slightly stretch them. And incorporating components from already the existing components that's commercially available, but then using new design of these structures, one can also build electronic systems that have some level of stretchability and also flexibility. So this is the engineering approach that has been quite successful and already show some applications. And currently, electronic skin is not limited to only measuring human sense of touch, but also one can think about incorporating various different chemical sensors. So these kinds of structures are chemical sensors. These are, again, chemical sensors. And they can be used to measure, for example, hormone or cytokines from saliva, sweat, and also interstitial fluid. And also, people are miniaturizing ultrasound to be placed onto body. So this is now actually a very active area of research, and especially combining with AI, a lot of the data collected can be made sense using AI. So again, you can see many rigid components are still needed in these kinds of devices. They are also considered in the general category of electronic skin. But the electronic skin we want to build, we want to start from the ground up. Basically, we want to fundamentally change the materials that are actually used in building this electronic skin. So this is an example of the type of electronic skin that we build in my group. These are made with materials that we design from molecular level and figure out how to make them have the right electronic properties, and then incorporate into sensors, integrated circuits. I mentioned about computing. So these are actually integrated circuits that we can build with the new type of materials. And then you can see they all take the form factor of human skin. They are stretchy, and we also have the self-healable counterparts and also the biodegradable counterparts. So these are all through understanding of the chemistry, the molecules, and how we design them to enable these electronic skin. So we also call them skin-inspired electronics, and the materials that are utilized in these devices, we call them skin-inspired materials. So you may ask, what's the fundamental difference between these materials and those used in conventional silicon electronics? What makes these materials we're using to be flexible and stretchable while silicon is rigid? If you look at them, these two types of materials from molecular level, actually it's immediately apparent. So on the left, these are polymers. So these are the type of molecules, general class of molecule that we work with. Basically, these are long chains of many, many different atoms that are linked together. They have many different conformations. They can adapt to many surfaces, and they are stretchy because these long chains, they have different conformation. You stretch them, you reduce the degree of freedom, and then they can be aligned and straightened. The problem is, for these molecules, they are really good at making insulators. They are great insulators like rubber materials, and we even use them as the insulator for cables to insulating copper or metal from touching each other to get short circuit. They are not good electronic materials. And on the other hand, you see silicon, the atomic structure of silicon. It's very rigid. The diamond lattice makes this material very rigid, and also as the single crystalline material, that's the perfect semiconductor, but you have to dope it with impurity to make them ranging from semiconductor to conductor. But this crystal structure, this arrangement of the atoms, makes the silicon intrinsically very brittle and very rigid. And then what's the difference if we use these different materials to make devices? Well, if you use the rigid material, so we define rigidity of a certain material or the intrinsic kind of not rigidity, intrinsically how hard a material is by using modulus as the parameter. So silicon has a parameter of a few hundred gigapascal. And the typical plastics, the modulus is also very high, almost in the same order of magnitude as that of silicon. But if you make them thin into almost like a thin film, even silicon can bend, but they can crack very easily if you bend them with too much curvature. On the other hand, the type of material we call skin-like, these are soft materials with modulus in the range of kilopascal to megapascal. So these are orders, many orders of magnitude smaller or lower compared to that of plastics and silicon. And then if you look at the human tissue and the organ, their modulus, bone is the highest, 15 gigapascal, still 10 times lower than silicon. And then as we go to skin or heart or brain, you can see the modulus is very, very low, kilopascal. So kilopascal is the range similar to firm tofu, for example. So very, very soft, or similar to jelly. So if you put something that's this hard, like silicon or plastic, into human tissue, they can cause scar tissuing formation. Even though these electronics can bend, but still just like paper. Paper can bend and fold, but the edge of the paper can still cut into our skin and cause a paper cut. So similarly, these edges can cut into the tissue and cause damage and form scars. So they could potentially, if we want to sense information within the body, in the brain, this scar tissue will block the electrical signal and the chemical signal. And if we want to place the devices, electronic skin, on the surface of the human body, then because they are quite rigid, then they will constrain the movement. That's why the engineering approach is to make these serpentine-like structure or wavy structure so that they can have some degree of stretchiness, not to constrain the movement. But if we use these soft materials, they should be naturally compatible. However, the challenge for us from the basic science aspect is how do we actually make the electronic materials to have softness similar as jelly, but at the same time, their conductivity or semiconducting property as good as silicon. Probably not the state-of-art NVIDIA processors, but at least in a level that we can do computing on the body and do some pre-data processing on the body. So this really sets a huge challenge from the materials point of view, but that's exactly what we want to be pursuing so that we have a lot of interesting problems we can be working on. And it turns out, so I mentioned that for polymers, they are too flexible. They have too many conformational kind of a disorder and many conformations. So, and also energetically, they have a very large energy gap, or we call band gap, that doesn't allow electrons to be excited into the right energy state for them to be able to transport, or they get trapped easily by impurity traps or some kind of structural defects. But it turns out, actually many years ago, several scientists, Heeger, McDermott, Shrikava, they were the people who discovered the conducting polymer. Their discovery was that having these rigid molecular structure, but making These are carbon-carbon atoms. And then between these carbon-carbon chains, if the bonds linking them together are these double bonds. In chemistry, we also call sp2 type of geometry. Then there are electronic states that can actually delocalize through this entire molecule. And also, this makes the energy level to be accessible for charges to be put into these molecules and also generate free charges to allow transport of electron or hole in these materials. But they are rigid molecules and also, again, brittle molecules. And in my early career, when I started in Bell Labs, actually my first experiment was to look for semiconducting polymers. And then our design was also inspired by the conducting polymer, the rigid design. But we thought that it's very important for the semiconductors to also be able to transport charges by having good overlap between these molecules so that the charges are not staying just within one molecule, because in a transistor, the size of the transistor is so that they are millions of times actually longer compared to the length of a single molecule. So it's not possible, especially at that time, for a single molecule to be able to conduct between two electrodes. So we have to rely on these charges to go from one molecule. So these lines are molecules, essentially these long lines. And then these electrons have to jump from one molecule to another, and then eventually go through the macroscopic electrodes. So that's why we thought not only these molecules need to have this double bond, single bond structure, but also we need to make them very regular in their molecular design so that they can form these ordered domains and allow electron to transport efficiently. But even then, you see, this is a kind of a schematic drawing of what the solid state molecular structure actually looks like. I draw a lot of these kind of banded and folded chains. That's because in nature, everything wants to go into the spontaneous direction, right? The law of thermodynamics. The spontaneous direction for these molecules to exist is to be more disordered. So even though there are some ordered structures, but still these molecules, they're made with many, many repeating units. So they want to twist against each other. And also when they are very long in length, they start to bend. And this actually slows down the charge transport. The charges can move the fastest along the straight line if they are perfectly planar, like a highway. But if they bend, this is like a traffic jam, then electrons cannot move quickly enough and then slow down the charge transport. So our goal in terms of the molecular design is first we need to understand what is causing this. And then we want to know how we can design molecules to circumvent these problems. So from molecular design, we can think about making molecules to have architectures that can maintain the rigidity and allow the charge overlap between these different chains. So this is one of the design we work with, we call molecular spring. Because if you think about it, if we want to make something rigid to become a stretchable or compressible material or unit, spring is what's come to mind the first. The spring is made of rigid metal, but you can stretch a spring, you can also compress it. So our idea is, can we make molecules like spring? So these are the repeats of the molecules. Then we have to build them up unit by unit. But these are the organic chemistry that we learn to perform over the years. And then this is what the structure of the molecule looks like. And these kind of big globe blobs of cloud. These are to represent the electronic cloud of to illustrate how much energetic overlap between these different layers of molecule. So this modeling actually is showing us that these type of design of molecules can have not only charge transport along these rigid molecule chains, but also in between these clouds are overlapping with each other. So we can potentially actually observe a new type of transport through these spring-like molecule. And they can also potentially, just like our macroscopic spring, they can be compressible and stretchable. So this is a version of or example of the type of molecules we're building. Took us quite a number of years. That's why I list so many students, several generations of students to make them. Now we can make them in gram scale. So now we're moving into actually studying these molecules, their individual molecular properties and macroscopic property. So this is still a ongoing project in the group. And then on the other hand, we can, I think I'll skip some of the slide for the time. On the other hand, another way to achieve the properties that we need, for example, semiconducting property and stretchability, or semiconducting property and self-healing. Another approach could be a way of thinking about it is if you mix two materials. Each material, the yellow one is the semiconductor, for example. The blue one is a stretchable elastomer insulator. Then if you mix the two, it will form a blend. And in the nanoscale, this would be how these molecules will phase separate and form this kind of interconnected network. And the domains will be nanometers or tens of nanometers. And then you potentially can get both properties. The yellow one will conduct the electricity, and the blue one support the yellow one, and when you stretch, it will not break the yellow one. But the only problem is here you can see only about 50% of the film is covered with the conducting material. So that means in the same thin film, I'm cutting down the electrical current essentially by half. So that means it's really degrading the properties of the material that we are trying to develop. But actually, a lot of the times in science, sometimes you have an idea, you think, well, it may work or may not work, but the courageous students, they decide, well, let's just try it. And then I'm also curious what will happen. So let's just see what will happen. And then sometimes unexpected things actually occurs. So this is one of those cases. My two postdocs, Jie Xu and Si Hong, now they are married. Actually, they work on the project together, and now they are married, and they are both faculty members at University of Chicago. So in my group, they were the two courageous people who decided to try this. They pick a semiconductor, they pick a insulator that's stretchable. And we pick these two because we know that they are not going to separate into layer structure, which will not give us the desirable kind of interconnected network. We choose them to have the right surface energy so that we expect the previous type of morphology. But to our surprise, so they made transistors, which is the basic building blocks that's used for making any integrated circuits. That's also the way we tested the electronic property of our materials. So the charge carrier mobility is incorporating this material into a transistor. And then we measure within the transistor how fast fast charge carriers can move in the thin film. The faster this is, then the faster the integrated circuit. Eventually, when we build them, they can perform different functions. And for amorphous silicon, the charge carrier mobility is actually below 1. So for these materials, their charge carrier mobility is already exceeding that of amorphous silicon, entering the regime of polysilicon, which can allow them to potentially make circuits that goes to megahertz and tens of megahertz speed and can perform useful functions. So Jie and Sihong, they made these transistors and measure their mobility, and these are different conditions that they use to make the transistors. So the first one was the mobility that they used just the pure semiconducting material to make the transistor. And they found that the charge carrier mobility is what's expected. It's decent value, better than amorphous silicon, as I mentioned. And this is what we already know. But what surprised us was that when they used 70% of insulator in the mixture, actually we made this film, it shows a charge carrier mobility even better than without any insulating material. So this is completely unexpected. My hypothesis was that we should reduce the mobility at least by half. I expect maybe at least an order of magnitude, because also these polymers, when they're separated by insulator, even if the domains are somewhat connected, the insulating molecule can get in between the semiconducting ones, also further block the charge transport. But here we saw actually an improvement. And then we can also use different ways. So this is a blade that's used to coat the film. Jie and Sihong also tried different ways to coat the film, and they keep seeing, wow, the mobility keeps going up, and they can get so much better performance than any of the other neat semiconductors that we already know in the field. So that was really exciting and also very intriguing why this is happening. So when we look at the film, and this is using atomic force microscopy to look at the films at nanoscale. And we saw that the film made with just pure component, pure polymer, it almost is featureless. You just see these nodules. That's an indication of the material is completely disordered. There's a very little crystallinity and not much kind of alignment or ordering of these polymer chains. But then the one with a blend of 70% of insulator, we see all these nanostructures that are forming within the film. So that's giving us some hint. Somehow these molecules are arranged in completely different ways when we make the blend. So we further studied these thin films, and we were able to leverage a technique that's called cryo-electron microscope. That actually the inventors of cryo-EM received the Nobel Prize for the ability to use this kind of microscope to image in the molecular level, even atomic level of biological proteins and enzyme. And also for material science, especially for polymer science, it also opens up a new possibility, because our molecules are similar as biological molecules. They're very easily damaged by electron beam. So the cryo-EM basically freezes the sample to cryogenic temperature. Then the electron beam will not cause damage so quickly. Eventually still damage, but it slows down the damage. So basically we froze up the solution that we used to make the thin film that we saw to have the improved charge transport and those nanostructure. We want to see that what is happening at the solution stage, and then what caused the solution. Is there any difference in the solution stage already in this neat film, a neat solution of the polymer and the blend solution? And how come it becomes different, completely different thin film structure when we eventually put them, evaporate the solvent? So the cryo-EM allows us to freeze the solution, and then we look into these films. So for the pure polymer film, then you see some of these some line-like structure. It's because this, you see the scale is a very, very small scale, 20 nanometer scale bar. So it's not very easy to see clearly, but these lines are actually individual polymer chains that we are able to now image. It's really incredible that we can actually directly see these molecules nowadays, and really provides new insights that we didn't have previously. And you see some of these molecules, they're not very long, maybe a little bit longer than 20 nanometers. And then some of them are parallel to each other. And this is actually what we call pi-pi stacking. This allows the electronic communication between these polymer chains. But there are only very few of these, and they are sparse. Here I can find a little bit, but then rest of the region, I just see some of these dots. Maybe the polymer actually is folded into other configuration. That's why we don't see these lines. Then in the blend solution, you can see, we see these much longer, larger structures. And these molecules are lined up within these structures, and then we see additional ones. And that's indicating that actually in the blend solution, when we add another substance into the material to make a mixture, actually this is already driving the molecules, the semiconducting molecules, to phase separate. They want to be together with each other. They don't want to be completely mixed with the insulator that's surrounding them. So then now they start to form this nanostructure. But in the nanostructure, you see the polymer chains are lined up. This is exactly what we want for charge transport, as we don't want them to fold. If they fold, charge transport gets slowed down. And if they line up and become straightened, this allows charges to go through very easily along the molecule and between the molecules. And then what happens when we dry up the film? So this is the dry film at very high resolution. So with the neat polymer, the one that shows almost no feature in this thin film, you can also again see almost no features in these in the high resolution, again suggesting highly disordered structure. But then the blend structure at high resolution, we see these long connected fiber. And then if we use even higher resolution, the neat one, you see the dots, not aligned structure. But then the high resolution of the blend film, each of these fibers consists of now those smaller nanostructure now come together. They become many of these aligned molecules, actually parallel to each other. So essentially, what is happening, kind of, we didn't expect this, but what's really happening is when we make this blend, in the blend, the two type of molecules, they will phase separate. And the phase separation makes the nanofiber-like structure. And these fibers are interconnected so that charge transport can still go through this film from the left to the right. But within these fibers, these molecules actually, in order to fit into this nanostructure, they come together. They are forced to become more planarized. If they are twisted, then they cannot come densely packed together. And also, if they are bending and folding, they cannot align along the lung axis. So they actually become more aligned and more planarized. And at the same time, this is really the key to increase charge transport. So that's really exciting because kind of now we have a very simple approach. Sometimes the solution may not be the most complicated one. This is actually a very simple approach. We have a lot of years of knowledge of how to design the neat conjugated polymers, but their charge transport was always lousy. But somehow when we add another polymer, now they become excellent materials. And then these matrix, they not only can be stretchable, we can also replace them with self-healable materials or biodegradable materials and photopatternable materials. So that's exactly what we did one by one, essentially kind of add skin-like properties into these materials without having to resynthesize new type of semiconducting polymer or new type of conductors. So nowadays, we have all these materials available to us, and that's the basis for us to build integrated circuits. The conventional integrated circuits are rigid, like shown here. These are silicon wafer, fabricated on silicon wafer using silicon. Our integrated circuits, we still use the patterning technique that's developed for semiconductor industry and for display so that our materials are compatible with those processes and then allow us to build these circuits. So this is our circuit on a piece of skin, on human skin. And then within these, we have now the 5th generation has been realized recently with gigahertz operation of transistors and CMOS integrated circuits. And they have the density, so individual small dot is a single transistor. Our transistor is not as small as the TSMC transistor. Our feature size is in the micron feature size, but those are sufficient for these large area fabrications and the large area applications. So our latest can have 1 million transistor per centimeter square type of density. And remember, these are still students, hardworking students working in the lab to make these integrated circuits. So I'm very proud of them to be able to make that achievement to really push the limit of what organic materials and what polymer materials can do. And with these kinds of materials and fabrication, now we can start to have fun and build electronic skin. This is one version that was reported in 2024, where we have in this small area, a few millimeter by a few millimeter area, we have 256 pixels, including the sensor and the transistor, so that can read out each pixel of the sensor. And the two students have shown, Donglai and Zhenan, have shown that they can actually collect the signal that exceeding the resolution of human skin. Now Donglai is in TSMC, pushing the limit of next frontier of semiconductor industry, and Zhenan took a faculty position in Purdue University. And another aspect that we want to be able to show is that our electronic skin can perform some level of simple computing and signal processing now. This is what Wei Chen has built. And in this case, we have integrated circuits incorporated into the e-skin, and then sensors combined with the integrated circuit basically output signal that are spike train signal, similar as what our human mechanoreceptor do. And here you can see with higher pressure, these are higher frequency of spike train signal. And then we also tested whether this type of signal can directly communicate with the brain, just like our sensory function of the skin. And he put these signal directly through the sensing of pressure and input into the brain of a mouse. And he was able to record the projected electrical signal that go from the somatosensory cortex into the projected into the motor cortex, and found that that signal can be used to stimulate muscle movement. So basically complete the loop of sensing and also actuation, similar as the human skin. And furthermore, Wei Chen was the one that pushed the limit of making these integrated circuit to 1 million transistors per centimeter square. So he and Yating and Mohammed are the 3 people who spent several years to achieve this. But now the individual circuit, so each of this square actually consists of a small circuit that can perform the same function as neuron, our neuron performance. So then in a few years, we hope that if we link these neuron circuits together, then we can also learn to perform some simple computing similar as our human skin. So then the e-skin, of course, one of the important applications is in robotic application. Currently, these robots do not yet have the sensory function to sense pressure, to sense touch. So the vision allows the robot to be able to see the object. But when the object is deformable, it's very difficult to predict using modeling how this object might deform, especially if you don't know the content inside the object. Then it's very hard to predict the deformation. And then with vision, it's not fast enough to respond to figure out what is really going on. That's why the soft toy gets dropped. So with e-skin, now we are building the whole hand of e-skin so that we can learn how humans actually interact with the surroundings and how we grasp different objects. For example, this is an antelope that my student Chen Yi now started a faculty position in University of Alabama. Bai Yu is still a graduate student working on the project. So they mounted the e-skin they built. Now we can have hundreds of sensors on the entire hand, and those different colors represent the different amount of force the electronic skin is experiencing. And then they can use this kind of e-skin, which doesn't interfere with our human sense of touch, to naturally grasp different objects. So they actually also work with other students together, collect tens of hours of data from grasping. This is just a few examples, but they collect the data of more than 40 different objects and then train the algorithm. So with these data, we can also see, well, why do humans use 5 fingers? Why we don't just have 2 fingers or 3 fingers? This is to show that we use the data of the 1 finger or 2 finger or the full hand to train the algorithm, and then use the algorithm to recognize objects that the glove is picking up. So if we just use the data from 1 finger, the accuracy is quite low. But if you use 2 fingers, it starts to become more accurate. 3 fingers almost saturate, and that's why actually you see a lot of grippers that have 3 fingers. It achieves the highest possible accuracy or good accuracy with least amount of hardware engineering. But if you have 5 fingers, it's slightly improved. Whole hand improve a little bit more, but not so much. So I think that our hand that have 5 fingers is mainly 3 fingers for sensory, but the other 2 is to help us to hold larger objects. But some level of sensory feedback, of course, is necessary. But if to perform simple function, just 3 fingers is enough. So this can also be used for us to think about for robot hand design, how we can design them to be most accurate, but also to be most energy efficient at the same time. What about for medical applications? I said we wanted to also measure human health, understand the human health. How can e-skin help that? Well, of course, e-skin is for putting on the surface of the body. It's 2-dimensional, very large coverage. So it can measure electrical signal from the head, the muscle electrical signal from the body, or even measure chemical signal in the sweat. But the real information, the real data, precise data is inside the body. That's where the information is generated. But if we want to get inside the body, what's available are these, again, very rigid devices that are still invasive. So what we need are the 1-dimensional structures, needle-like structure, but we want to make them soft so that these structures can be minimally invasively implanted into the body, cause very little damage. I watched a neurosurgeon placing the deep brain stimulator into a patient. Actually, to my surprise, the surgery room is not so much kind of worse or bloody compared to a dentist office. Patient is just sitting on a chair that can lie down, and all kinds of tools around. And there's only a very little hole. It's opened on the skull, and very little blood can be seen. And I was really stunned by how advanced the medical surgery is nowadays. That's because they are using 1-dimensional probes that's implanted into the brain. So I really believe if we can do that, then it's possible to have many more, to open up many new directions for understanding human health, to get inside the body. But to make these devices, it's very challenging. We need sensors to measure the brain electrical signal. We need not only 1 electrode, we need thousands of electrodes to go all the way deep into the brain. They have to all fit into this little string. It's very hard to put them in there. Currently, people use state-of-art TSMC technology, again, silicon. That's well established. So for technology development, always people go back to silicon. This is one of the most advanced neural pixels made by IMAC. They have thousands of electrodes that can record at a single neuron level. But you need TSMC type of fabrication to make them because it's hair thin. To fit in so many components and wires, they need each wire to be in the tens of nanometer scale. And you can also make fibers, draw fibers. But for fiber, you can only put sensors in the tip. You cannot put along the side. And there also have been attempts to make soft material probes. And here you can use multi-layer fabrication. So each layer can make 9 probes. If you make 10 layers, you get 90 probes. But you can see that's many, many steps to make a probe. And that's prone to defects, and just the cost is too high. And people also use nano patterning, the most advanced electron beam patterning, which is not a tool that's at industry scale, even though these nanometer size of features can be made. So in our case, since we have electronic skin, they are made with unconventional electronic materials. They can tolerate strain. They're bendable, foldable, and stretchable without degrading the electronic property. So when Mohammed came to my group, he said, "Oh, I really want to do something that's impact the human health, implantable devices." So I said, we have to think about how to make e-skin into this one-dimensional structure. How about let's just fold it up? So he was able to really develop the process and take the e-skin, now turn into one-dimensional structure, actually just by rolling. It looks simple, but there are a lot of material science, a lot of materials chemistry going to making these kinds of devices and also engineering the sensors. So these are essentially jelly rolls, but with sensors exposed on the surface and also sensors embedded inside, and all the wires are embedded inside. That's why we can have really small form factor in these fibers. Nowadays, the fibers can measure a range of things. So we're particularly interested in the brain, how the brain functions. So that's why we designed these sensors to measure neurotransmitters, such as dopamine, serotonin, which help us to understand the reward of the brain and also linked to the mental health. Cortisol is a type of hormone that regulates many functions of the body, but if we are stressed, the hormone level will go up. And also, if cortisol is too high, then melatonin is going to go down, then you cannot sleep well. So these are all linked to each other. Now we have sensors, so we want to be able to actually measure what's the correlation between these chemicals we can measure in the brain and what's on the body and what's in the peripheral. So there are many sensors we can now already make and measuring the guts, the brain, the heart. One exciting one that I want to mention that is really unique about this NeuroString that no conventional sensors can really do is the softness of the NeuroString. So this is the NeuroString. And this is the system that we made for testing to see if our NeuroString implanted inside the intestine of the pig, whether we can pick up electrical signal, movement of the gut, and the serotonin, because this information actually indirectly reflect the function of our brain. Our gut is the second brain. It has a lot of neurons actually inside the gut, and the gut health will impact the mental health and the overall health of the person. But the NeuroString, because it's soft, it can stay inside the gut without causing any damage or discomfort, and therefore allow for the first time for us to perform these measurements in live-awake animal without, these animals do not need to have anesthesia because there's no uncomfortableness. And then we can start to track data inside the gut over period of time. The initial experiments is over week-long continuous measurement. These are measuring the movement of the guts. We saw circadian rhythm, and now we start to track also serotonin measurement, and these are different kinds of signals so we can start to measure. So it's very exciting that these are providing new information that's never seen before. This is one experiment that really represents, I think, where we want to go in the future. In this experiment, we implanted one NeuroString in the brain that allows us to measure neurotransmitters and the electrical signal. But at the same time, there is a NeuroString that's implanted inside the intestine in this mouse. And this mouse is awake. You see the eyes are open. It can freely move around, but we can measure the serotonin in the gut as well as the neurotransmitter in the brain simultaneously. So now for the first time, we can start to see how these neurochemicals impact each other when the brain sends information. When does this information actually gets to the gut? And then when the gut is feeling something or have discomfort, when does the information gets to the brain? So to summarize, here, what we have been pursuing started from electronic skin and then now moving into one-dimensional NeuroString. And this bigger kind of dream and the bigger direction really is what motivated us to design new materials, understanding the chemistry, and design materials from ground up. And now it's enabling possibilities, not only in the robotic field, but also in human health. So I'm very excited that I have the opportunity to share this work and this journey with you. But of course, it would not have been possible without all the students, past and the current student. This is my current research group, very interdisciplinary group with people from chemistry, chemical engineering, material science, electrical engineering, mechanical engineering, bioengineering, and also MD, PhD, and the computer science. And it's really kind of wonderful for me to have the opportunity to learn all throughout my career together alongside with my students and also learn from many of my colleagues who I collaborate with in different departments and in different disciplines and also supporting funding from different agencies. Thanks again for having me, and I'll be happy to answer questions. Thank you.
Okay. Well, that's a spectacular work. I really enjoy it. Let's see questions. Yeah.
Thank you so much for the opportunity, Dr. Bao. I am actually going to ask a question about the prospects of eventually doing clinical longitudinal study of having the artificial skin on the patient's body for a long time to see if it will eventually integrate correctly into the patient's own body and perform the regular duties as like any regular skin. And also I wanted to know what the prospects of transplanting the artificial skin into like human stomach membranes, because in the stomach there's like acids, so the environment is a lot different from like the outside. So are there any like alterations that are needed on the human skin if we want to try to test it like on the inside of human body?
Yeah, thank you for the questions. The first question is about the prospect of measuring from the surface of the human body, and also whether it's possible to wear these devices over long term. Well, everything will start from first a simple application and applications that are feasible to then more challenging applications. Certainly, the shorter the duration, the less requirement on the robustness of the devices and also the biocompatibility of the devices. So I think we're inspired by the continuous glucose monitoring devices that are already used by millions of people for measuring blood sugar level. And I think that kind of format will be a very good starting point for measurement of other chemical species from the body and without much damage to the body. And in that case, it's about 2 weeks of measurement. And then after that, when we'll replace the sensor, mainly because the sensor can still drift, as well as there can be scar tissue formation, which blocks the signal. So for many of the wearable application, I think that would be a good format. And then for brain implantation, that I think will be the most challenging, and also implantation for 10 years or even longer, that will be extremely challenging. So the pathway before getting there is to have applications that are intraoperative. For example, during brain surgery, actually the surgeon needs to measure the electrical signal to know where to implant the probe. Then afterwards, the sensors are removed after the surgery. They are not left inside. So this could be the initial path to allow the sensors to be tested in human, and then to make sure they're reliable enough. And then the next stage are applications, for example, epilepsy patient. They now try to find where the center of the brain that's generating these irregular electrical signal. The patient stays in the hospital for a week and have multiple brain probes implanted. Then after a week, these probes are removed. But now the probes are very low resolution, and sometimes still, even after a week, the doctors cannot find exactly the brain region responsible for the epilepsy in order to perform the surgery. So these are, again, great opportunities for the early entry of a new technology. Then eventually, when they are proven, eventually people are going to be more comfortable, and also FDA may eventually approve the safety of these devices. So that is going to be a long path to get there.
Okay, second questions.
Professor Bao, thank you for the so inspiring talk. So I wonder, can you comment on how do these internal implants get power delivery? For example, through just absorbing glucose or other kind of energy by like synthesizing some kind of polymer that can take energy directly from our body?
Yeah, so powering is always a challenge. It's another challenge that we are not directly addressing ourselves. The electronic devices can potentially be wirelessly powered externally, but it seems that even though it looks more kind of biocompatible, have a lesser size, smaller size of electronics, but clinically, it seems doctor rather have a large implanted battery in the body, because patient will not have to worry about doing any measurement or make sure their battery is charged for any treatment. So that's one way, and also miniaturizing the battery is another need, definitely. But that area of research, I think, is still quite under development, because most of the funding is for electrical vehicle, not so much for the medical batteries.
Thank you.
Other questions?
Oh, there's one in the back here.
Oh.
Okay, thanks, Professor Bao. Thanks for your very excellent works. I have two questions. The first one is about the charger carrier mobility. We know that you have used many different ways to improve the charger carrier mobility, but we know that the charger transport efficiency of the polymer materials is fast, smaller than that of the single crystal material like the silicon. Do you have some general ways to improve the charge transport efficiency or theory, like the how to control the bond gap to other people, and then we can make or design some very high charge carrier mobility materials. This is the first question. And the second one is about the bioelectronic fiber. The electronic device very small, but we should put some sensors, antenna, or some very high frequency digital together. But we know that when it works, the high frequency current will generate the electromagnetic wave, and it will influence with each other. How to
Could you
and at
short-
time, okay, how to avoid the electromagnetic interface or capability? Thank you.
So the first question is on whether there is a possible design that really can boost the charge carrier mobility of organic electronics to another level. I think ultimately, if one can have a single molecule conducting and the single molecule doesn't have the conformational disorder I mentioned, and then the charge injection barrier is low enough, it's ohmic contact, then we will have the kind of essentially single crystalline silicon level of charge transport would be possible. But that's still very, very challenging from the synthesis, molecular design, and also the engineering side. And then the second question is, I forgot what's the second question, but one sentence summary of the second question.
I mean, because the electronic device very
Oh, the
small.
electromagnetic
Yes.
field, yes, interference. Well, I'm glad now we are kind of going to more considering the practical problems and not at the beginning is whether this kind of thing is even possible to be made. So the electromagnetic field, then that would be requiring some level of creative engineering design, but I think that's not my area of expertise. I'm not an electrical engineer, but I think working with the electrical engineers, it's possible to solve the problem.
Okay, great. Thank you very much. I think we should stop.
Thank you.
Yeah, thank you.